On December 14, 1972, Eugene Cernan climbed the ladder of the Apollo 17 lunar module and left the surface of the Moon. He was the last human being to stand on another world. He has been the last human being to stand on another world for more than 50 years. Think about what that means in terms of the actual calendar. The year Cernan left the Moon, the Vietnam War was still ongoing. Richard Nixon had just won re-election in a landslide. The World Trade Center had just been completed. The personal computer did not exist. The internet did not exist. The first cell phone call would not be made for another year. Voyager 1 would not launch for 5 years. Everything that has happened in human civilization since December 1972, every technological revolution, every political upheaval, every cultural transformation, the entire digital age, the entire information age, the entire history of the modern internet has happened while no human being has been farther from Earth than low Earth orbit. We have not gone back to the Moon. The question is why? And the answer, the real answer, not the simplified version that involves budget cuts and political will and Cold War priorities, is more complicated and more interesting and more disturbing than most people know. Because the reasons we did not go back are not just historical facts about 1972 and 1973. They are facts about what we are as a species, what we value, how we make decisions about enormous collective investments, and what it actually takes for a civilization to sustain the most ambitious thing it has ever done. Tonight, we are going to think about this carefully, not as a political argument, not as a lament, as an honest examination of what happened, why it happened, and what it means that it happened. If the night is long, stay. Start with what the Apollo program actually was, because most people's mental model of it is wrong in ways that matter. Apollo is often described as a triumph of human exploration, a testament to what humanity can achieve when it sets its mind to something, the fulfillment of an ancient dream. These descriptions are not wrong, but they are incomplete in a specific way. Apollo was a weapons program that landed on the Moon. Not in a conspiratorial sense, in a straightforward historical sense. The Saturn V rocket that carried Apollo astronauts to the Moon was the culmination of a missile development program that began with German V-2 rockets in World War II, continued through the development of intercontinental ballistic missiles in the late 1940s and 1950s, and was repurposed for space exploration when the political moment made space exploration a tool of national competition. The engineers who built the Saturn V were the same engineers, or the students of the same engineers, who had built the rockets that were pointed at cities. Wernher von Braun, the technical director of the Apollo program, had been the technical director of the V-2 program at Peenemünde. The infrastructure, the knowledge base, the manufacturing capacity, all of it was dual use, developed primarily for military purposes and applied to moon landing when that application served political goals. This is not a criticism of the people who built Apollo or the astronauts who flew it. It is a statement about the political and industrial context that made Apollo possible. Apollo was possible because the United States was engaged in an existential competition with the Soviet Union, and that competition was expressed in part through rocket development. And rocket development was funded at levels that peacetime science budgets never approach, because it was understood as directly relevant to national survival. The NASA budget at its peak in 1966, when Apollo was in full development, was approximately 4.4% of the federal budget. In today's terms, proportionally scaled, that would be something like $180 billion per year. The actual NASA budget today is approximately $25 billion per year, less than 1/7 of the Apollo-era proportional equivalent. The money was not about the Moon. The money was about missiles. The Moon was what happened when you had that much money and that much missile technology and a political moment that made going to the Moon symbolically essential. When the political moment changed, when the Soviet space program faltered after losing the moon race, when the Vietnam War consumed political capital and domestic attention, when the cultural upheavals of the late 1960s shifted national priorities, the money stopped. Not immediately, not all at once, but systematically across a series of budget decisions beginning in 1967 and continuing through 1972, the Apollo program was dismantled faster than it had been built. The Saturn V production line was shut down in 1968. The last Saturn V was manufactured in 1968, even though the last Apollo mission using it flew in 1972. There were Saturn V rockets sitting in storage, assembled and ready, with no missions planned for them. 3 planned Apollo missions, Apollo 18, 19 and 20, were cancelled between 1969 and 1970. These were not cancelled because the moon was fully understood or because the scientific goals of the program had been achieved. They were cancelled because the budget was cut and the political will to continue was gone. The decisions that ended the moon program were made while men were still standing on the moon. This is the first and most important thing to understand about why we never went back. The program was cancelled before it was finished. Now let us think about what this means technically, because the cancellation of Apollo had specific technical consequences that are still relevant today and that explain part of why returning to the moon has been so difficult for so long. When the Saturn V production line was shut down in 1968, the institutional knowledge embedded in that production line began to disperse. The engineers who knew how to build Saturn V engines retired or moved to other projects. The suppliers who manufactured components for the Saturn V reorganized around other contracts. The manufacturing processes that had been developed through years of trial and error were not fully documented in ways that would allow reconstruction by a different team decades later. This process, the erosion of institutional knowledge when a technology program ends, is not unique to Apollo. It happens whenever a complex technology stops being used. But the consequences for Apollo were severe, because Saturn V was not a technology that existed anywhere else in the world. It was custom-built for one purpose by one organization over 1 decade, and when that organization stopped building it, the knowledge of how to build it began to disappear. When NASA attempted decades later to understand how the F-1 engines that powered the Saturn V's first stage worked, as part of the Ares program and later the Space Launch System development, engineers found that some of the manufacturing techniques were simply unknown. The original engineers were mostly dead or very elderly. The documentation was incomplete. The production records had been dispersed to multiple archives, some of which were poorly organized. NASA actually had to reverse engineer components of the Saturn V, disassembling existing museum pieces and analyzing them with modern tools to understand how they had been built. The world's most powerful rocket, which flew successfully 13 times, had to be reverse engineered from museum artifacts. This is not a failure of record keeping, though record keeping was imperfect. It is a consequence of the fact that complex technology is not fully captured in documentation. It lives in the people who built and used it, in the tacit knowledge of machinists and welders and test engineers who knew things they had never written down because they did not know they needed to write them down. When those people are gone, the knowledge is gone with them. The cancellation of Apollo did not just end a program, it erased knowledge that cannot be fully recovered. Now let us think about what happened after Apollo, the period from 1972 to the present, through the specific lens of the decisions that were made and why. When the Apollo program ended, there were serious proposals for what should come next. The aerospace industry and the scientific community had developed plans for a sustained presence in space, plans that in 1969 and 1970 seemed plausible given the trajectory of the Apollo program. A space station in Earth orbit was planned, a large, permanent facility where dozens of astronauts would live and work. A reusable space shuttle to service it, a vehicle that would make access to orbit routine and inexpensive rather than requiring a new expendable rocket for each mission. A lunar base, a permanent human presence on the Moon, building on the Apollo landings to establish a research station that would operate continuously. And eventually, a human mission to Mars, using the Moon as a staging point, building on the lunar base, extending human presence to another planet. This was the plan. It was articulated clearly. It had broad support in the aerospace community. It had technical coherence, each step built on the previous, using the infrastructure and knowledge accumulated along the way. What actually happened was a negotiated compromise that preserved one element of the plan while abandoning the others. The space station was deferred, initially indefinitely, eventually until the 1990s, when the International Space Station program began under very different political and budgetary circumstances. The lunar base was abandoned entirely. The Mars mission remained a perpetual aspiration, repeatedly proposed and never funded. And the space shuttle was built, but built under budgetary constraints that required it to be simultaneously the workhorse of the entire space program, the military satellite launcher, the commercial satellite launcher, and the science platform that the cancelled station would have provided. The space shuttle became everything because everything else was cancelled. And in becoming everything, it became optimized for nothing. The shuttle was initially promised to fly at a frequency of 50 times per year and at a per-flight cost of approximately $10 million. It ended up flying at most 9 times in its best year, and at an average per-flight cost of more than $1 billion over the program's life. The gap between the promise and the reality was not a failure of engineering. The shuttle's engineering was extraordinary. It was, and remains, the most complex flying machine ever built. The gap was a consequence of the political decisions that preceded the shuttle's design. Budget constraints forced the shuttle to be designed around compromises that made it simultaneously more complex and more expensive than the original concept. The solid rocket boosters, the cylindrical rockets attached to the shuttle's external tank, were added to the design primarily to reduce the program's development cost, because solid rockets could be manufactured by a supplier in Utah whose congressional delegation had political influence over the shuttle's budget. The solid rocket boosters were responsible for the Challenger disaster in 1986. The design decisions that killed 7 astronauts in 1986 were made in 1972 in response to budget pressures and political negotiations. This is the second thing to understand about why we never went back to the Moon. The program that replaced Apollo was compromised from its inception by the same forces: budget constraints, political fragmentation of technical decisions that had ended Apollo. Now let us think about something that is not often discussed clearly: the specific role of the military in American space policy, and how that role shaped the decisions that determined the trajectory of the program after Apollo. The Department of Defense was a major stakeholder in the Space Shuttle program. The Air Force needed a vehicle to launch military payloads, spy satellites, communication satellites, early warning satellites. The shuttle's design requirements were modified to accommodate these military needs. The shuttle's payload bay was made larger, and the vehicle was given the cross-range capability needed to return from polar orbits used for military reconnaissance. These modifications added cost and complexity. They were not made in the interest of science or exploration. They were made because the Air Force's budget was needed to supplement NASA's insufficient appropriations, and the Air Force's price for contributing its budget was influence over the vehicle's design. The Air Force ultimately built its own launch complex at Vandenberg Air Force Base in California, designed for military polar launches of the shuttle. The complex was completed in 1985 and never used. The Challenger disaster in 1986 and the subsequent decision to stop using the shuttle for military payloads made the Vandenberg complex obsolete before it was ever operational. One of the most expensive launch facilities ever built was constructed, completed, and abandoned without launching a single flight. This is the kind of thing that happens when a technology program is driven by the political negotiation of competing interests rather than by coherent technical goals. Now let us think about the specific technical reasons why returning to the Moon has been so difficult in the decades since Apollo, because the political story is only part of the explanation. Returning to the Moon requires, at a minimum, a rocket capable of lifting the mass needed for a lunar mission into orbit. The Saturn V could lift approximately 130 metric tons to low Earth orbit. No rocket built since the end of the Saturn V program has matched this capability. The Soviet N-1 rocket, developed to compete with Saturn V for the Moon, failed 4 times in unmanned tests and was cancelled in 1976. The Space Shuttle could lift approximately 24 metric tons to low Earth orbit, less than 1/5 of Saturn V's capacity. No American rocket built between 1972 and 2022 exceeded 70 metric tons to low Earth orbit. The Space Launch System, SLS, which flew its first unmanned test in November 2022 and is intended to carry NASA's Artemis missions to the Moon, can lift approximately 95 metric tons to low Earth orbit in its current configuration. Larger variants, planned but not yet built, would eventually match or exceed Saturn V's capacity. But the development of SLS has taken more than a decade and cost approximately $23 billion for the first flight. By comparison, Saturn V was developed in 7 years at a total program cost, adjusted for inflation, of approximately $50 billion, covering 13 flights rather than 1. The cost per kilogram to orbit for SLS is roughly $20,000 to $30,000, orders of magnitude more expensive than what modern commercial rockets are achieving. SpaceX's Falcon 9 launches at roughly $2,700 per kilogram to low Earth orbit. SpaceX's Starship, currently under development and test, is designed to achieve costs of $100 or less per kilogram if its full reuse architecture is realized. Starship's payload capacity to low Earth orbit, when fully operational, may exceed 150 metric tons, more than Saturn V. The gap between government rocket development costs and commercial rocket development costs is not primarily a technical difference. It is an organizational and incentive difference. SpaceX develops rockets with a small fraction of the workforce of NASA's traditional contractors, with a culture that prioritizes rapid iteration and accepts failures as learning opportunities, and with financial incentives, the company's own money is at risk, that create pressure to find cheaper solutions. NASA's traditional contractors, Boeing, Northrop Grumman, Aerojet Rocketdyne, develop rockets under cost-plus contracts, where the government pays all costs plus a profit margin. Under cost-plus contracting, there is no financial incentive to reduce costs. Higher costs mean higher profits. The incentive structure rewards complexity and schedule extension rather than efficiency and speed. This is the third thing to understand about why we never went back to the Moon. The institutional and economic structures through which the United States conducts large space projects are poorly suited to achieving ambitious technical goals efficiently. Now let us think about what the Moon actually is, scientifically and practically, because understanding what was left behind when Apollo ended helps clarify what was lost and what has been missed in the intervening decades. The Moon is the closest celestial body to Earth. It is a world approximately 1/4 Earth's diameter, with no atmosphere, no liquid water on its surface, negligible geological activity, and a surface that has been largely undisturbed for billions of years. The last property, undisturbed for billions of years, is the most scientifically significant. On Earth, geological processes continuously recycle the crust. Erosion, plate tectonics, volcanic activity, these processes destroy the record of Earth's earliest history. The oldest intact rocks on Earth are approximately 4 billion years old, and rocks that old are rare and fragmentary. On the Moon, the surface has been preserved since the period of heavy bombardment that ended approximately 3.8 billion years ago. The rocks on the lunar highlands, the bright cratered regions, are 4.0 to 4.5 billion years old. They are samples of the original crust of a world, preserved intact since the solar system's early history. The Apollo missions returned approximately 382 kilograms of lunar samples. Analysis of these samples has produced fundamental insights into the formation of the Moon, the early history of the solar system, and the conditions that prevailed during the period when life was forming on Earth. The leading model for the Moon's formation, the giant impact hypothesis, emerged from analysis of Apollo samples. The chemical composition of the samples showed that the Moon is chemically similar to Earth's mantle, but lacks certain volatile elements that would be present if it had formed independently. This pattern is consistent with the Moon forming from the debris of a giant impact between Earth and a Mars-sized protoplanet early in solar system history. But 382 kilograms is a tiny sample of a world with a surface area of 38 million square kilometers. The samples returned by Apollo came from 6 locations, all near the equator, all chosen for landing safety rather than maximum scientific diversity. The lunar poles, the regions with the most scientifically interesting recent discovery, were never visited by Apollo. In 1994 and 1998, the Clementine and Lunar Prospector missions detected evidence of water ice in permanently shadowed craters near the lunar poles. In 2009, the LCROSS mission deliberately impacted a permanently shadowed crater near the South Pole and confirmed the presence of water ice, along with other volatile compounds, including sulfur dioxide, mercury, and silver. Water ice at the lunar poles changes the practical significance of the Moon for human exploration. Water can be electrolyzed into hydrogen and oxygen, providing both breathable atmosphere and rocket propellant. A lunar base near the poles could be supplied with water from local resources rather than bringing it from Earth. This discovery was made 37 years after the last Apollo mission. If Apollo had continued, if the lunar base planned in 1969 had been built through the 1970s and 1980s, the water ice at the poles would have been discovered and exploited decades earlier. The development of in situ resource utilization, the use of local resources to support space operations, would be far more advanced than it is today. Instead, we are discovering these resources now with missions that are delayed, underfunded, and technically challenged compared to what would have been possible with 50 additional years of continuous investment. Now let us think about what Russia was doing during the same period, because the Soviet space program's trajectory after the moon race illuminates something important about why sustaining ambitious space programs is so difficult. The Soviet Union lost the moon race. The N-1 rocket failed. The Soviet program never landed a human being on the moon. This was a significant geopolitical defeat, and it reshaped Soviet space strategy. After the moon race, the Soviet Union pivoted to a different approach: long-duration space stations. The Salyut program, beginning in 1971, and later the Mir station, launched in 1986, established a Soviet expertise in keeping humans in space for extended periods. Cosmonauts lived on Mir for months at a time. One cosmonaut, Valery Polyakov, spent 437 consecutive days on Mir, a record that stood until recently. This was not accidental. Long-duration space stations were a domain where the Soviet Union could compete successfully after losing the moon race, demonstrating capabilities that the United States did not have, and maintaining a visible presence in space without the astronomical costs of a lunar program. The Soviet approach produced genuine scientific knowledge about the long-term physiological effects of microgravity, about closed-loop life support systems, about the psychological challenges of extended isolation. Some of this knowledge was shared and incorporated into the International Space Station program. Some of it was lost when the Soviet Union collapsed in 1991. The collapse of the Soviet Union in 1991 had direct consequences for the space program. Russia inherited the Soviet space infrastructure, but with a dramatically reduced budget. Many of the engineers and scientists who had worked in the Soviet space program emigrated or left the field. The knowledge base, the tacit knowledge that lives in experienced engineers, was dispersed in ways that have never been fully recovered. Russia's current space program is a diminished version of the Soviet program. It has maintained the Soyuz capsule and rocket as a reliable workhorse for crew transport, and it has continued to contribute to the International Space Station. But its ambitions for exploration beyond Earth orbit have not been realized, and its budget constraints make it unlikely that they will be in the near term. The two powers that conducted the original moon race no longer have the technical capability to conduct missions comparable to Apollo. The knowledge has been partially lost, the infrastructure has been partially dismantled, the industrial base has been reorganized around different priorities. This is the fourth thing to understand about why we never went back. The knowledge and capability needed to return to the moon did not simply wait, preserved in storage, for a future generation to use. It degraded. Engineers retired, programs ended, knowledge dispersed. The task of returning to the moon is more difficult today than it would have been in 1980, not because the moon is more difficult to reach, but because the human capital and institutional memory required to reach it efficiently have been partially erased. Now let us think about something that is more fundamental than the political and organizational failures, something about human psychology and the specific challenge of sustaining commitment to very long, very expensive programs. Apollo succeeded in part because it had a specific, clear, measurable goal: land a man on the moon and return him safely to Earth before the end of the decade. John Kennedy's 1961 speech articulating this goal created a commitment structure that was, by accident or design, well suited to political sustainability. The goal was specific. There was no ambiguity about what counted as success. Either a man stood on the moon before December 31st, 1969, or he did not. This specificity made it possible to track progress clearly, to maintain urgency, and to hold decision-makers accountable. The goal was bounded. It had a deadline, the end of the decade. This created urgency and prevented the program from being deferred indefinitely in favor of other priorities. The deadline was also long enough, 8 years, to allow serious technical development, but short enough to be within the political horizon of the decision-makers who had committed to it. The goal was politically charged. The moon race was explicitly a competition with the Soviet Union, and the Soviet Union was explicitly an existential threat. This meant that failure to meet the goal had consequences that were understood as directly relevant to national security, not just embarrassment, but evidence of weakness in a competition that determined the balance of power between nuclear-armed adversaries. These three features, specificity, bounded deadline, existential political stakes, combined to create a commitment structure that could sustain the program through setbacks, budget pressures, and political transitions. After Apollo, no program aimed at returning to the moon or extending human presence beyond Earth orbit has had all three of these features simultaneously. The goals have been vague: return to the moon for science, establish a presence, develop capabilities for eventual Mars exploration. Vague goals are easy to redefine or defer when budgets are tight. The deadlines have been distant or non-existent, or when deadlines have been set, they have not been met, and the programs have been redesigned rather than cancelled. The Space Exploration Initiative announced by President George H.W. Bush in 1989, proposed a return to the Moon by 2004 and a Mars mission by 2019. Neither happened. The vision for space exploration, announced by President George W. Bush in 2004, proposed a return to the Moon by 2020. It did not happen. The Artemis program, announced with an initial target of 2024, has been revised to 2026 and may slip further. The existential political stakes have been absent. The Soviet Union no longer exists. China is a competitor, but has not created the same sense of urgency, at least not yet, that the Soviet competition created in the 1960s. Without an existential competitor, the political cost of deferring a Moon return is low. There is no immediate, visible consequence that creates urgency for decision makers. This is the fifth and perhaps most fundamental thing to understand about why we never went back. The conditions that made Apollo possible, not just the budget, but the specific political commitment structure that sustained the budget, have not been replicated. Now let us think about the specific moment we're in now, the Artemis program, the commercial space revolution led by SpaceX, the entry of other nations into the deep space competition. Because understanding the present requires understanding everything that came before it. The Artemis program is NASA's current effort to return humans to the Moon. It is named for the twin sister of Apollo in Greek mythology, a choice that reflects its goal of landing the first woman and the first person of color on the Moon. Artemis has made real progress. Artemis 1, the unmanned test flight of the Space Launch System and Orion spacecraft, flew in November and December 2022, completing a lunar orbit and returning to Earth. It was a genuine success, demonstrating that the SLS Orion system works and that a crewed lunar mission is technically feasible. Artemis 2, the first crewed test flight, is planned for 2025. It will carry 4 astronauts around the Moon without landing, a mission comparable to Apollo 8, the first crewed lunar orbit in 1968. Artemis 3, the first crewed landing, is planned for 2026. It will use the SpaceX Starship lunar lander to descend to the surface, the first time humans will stand on the Moon since Cernan in 1972. But the Artemis program faces the same structural challenges that have derailed every previous post-Apollo Moon program. The SLS costs approximately $4 billion per launch, a cost so high that launching it more than once per year strains any realistic budget. The Orion spacecraft, developed over more than a decade at enormous cost, is a capable vehicle, but not a revolutionary one. The potential game-changer is SpaceX. SpaceX's Starship, a fully reusable stainless steel spacecraft that is the largest and most powerful rocket ever built, represents a fundamentally different approach to space transportation. If Starship achieves its design goals, it would reduce the cost of putting mass into orbit by a factor of 10 to 100 compared to any existing rocket, including SLS. At the cost per kilogram that Starship aims to achieve, a Moon mission would cost a fraction of what Apollo cost. The Moon would become accessible not just to governments with enormous budgets, but to a much wider range of actors, including commercial companies, research institutions, and eventually private individuals. Starship is still in development. It has conducted a series of test flights, each one demonstrating more of the vehicle's capabilities than the last. The full stack, Super Heavy booster plus Starship upper stage, has flown several times, demonstrating booster return, hot staging separation, and various other technical milestones. The complete reuse architecture, both booster and upper stage returning to the launch site and being caught by the launch tower's mechanical arms, has been demonstrated. If Starship succeeds as designed, it will represent the most significant reduction in the cost of space access since the beginning of the space age. And it will make the question of why we never went back to the Moon obsolete, because the cost and technical barriers that have prevented a return for 50 years will be dramatically reduced. Now let us think about China, because the geopolitical dimension of lunar exploration has returned in a form that has real implications for the pace and priority of American lunar activities. China has been conducting a systematic and successful robotic lunar program since the Chang'e 1 mission in 2007. Chang'e 4 in 2019 was the first mission to land on the far side of the Moon, a technically challenging achievement that had never been accomplished before. Chang'e 5 in 2020 returned lunar samples to Earth, the first sample return since the Soviet Lunar 24 mission in 1976. China has announced plans for a crewed lunar landing, initially targeted for approximately 2030. The specific architecture involves a Long March 10 rocket, a crewed Mengzhou spacecraft, and a lunar lander. China has developed and tested components of this architecture, and the program appears to be proceeding on a trajectory consistent with a 2030 landing. If China lands humans on the Moon before the United States returns, if the Artemis program is delayed enough that the gap closes, the political implications would be significant. The moon race framing that has partly motivated Artemis would be validated by exactly the scenario it was designed to prevent. China's long-term lunar goals extend beyond a first crewed landing. China and Russia have signed a memorandum of understanding to develop an international lunar research station, a permanent robotic and eventually human presence at the lunar South Pole. The station is planned for initial construction in the 2020s and crewed operations in the 2030s. If this program proceeds as planned, the geopolitical situation on and around the Moon in the 2030s will be substantially different from the situation today, with two significant actors pursuing distinct programs, creating the potential for competition over the most valuable lunar real estate. The most valuable real estate on the Moon is the permanently shadowed craters near the poles, where water ice is confirmed to exist. These locations provide both scientific value — the water ice is ancient, potentially carrying records of the early solar system's volatile chemistry — and practical value as sources of water and propellant for human operations. The area of permanently shadowed craters near the lunar South Pole that contains confirmed water ice is limited. The number of locations that combine water ice accessibility with suitable terrain for landing and base construction, with the line of sight access to Earth needed for communications, and with proximity to sunlit areas for solar power, is small. There may be only a handful of truly optimal sites. If China establishes a permanent presence at one of these sites before the United States returns, the question of access to that site becomes complicated. Space law, specifically the Outer Space Treaty of 1967, prohibits national appropriation of the Moon, meaning no country can claim sovereignty over lunar territory. But it does not clearly prohibit the physical use and occupation of specific locations, or the extraction of resources from those locations. The legal framework for managing competing national interests on the Moon is thin and untested. The Artemis Accords, a set of principles articulated by NASA and signed by a growing number of countries, address some of these issues, but China and Russia have not signed them and do not recognize their authority. This is the emerging geopolitical landscape of the Moon, one that increasingly resembles the territorial competitions of the early Antarctic exploration era, with similar ambiguities about rights, access, and the enforcement of international agreements in the absence of any effective international authority. The competition over the Moon is not just about flags and footprints. It is about water ice, about resource access, about the practical infrastructure of sustained operations at the most useful locations on a world that will become increasingly important as humanity extends its presence into the solar system. Now let us think about something that is rarely discussed in the context of why we never went back: the specific psychological and cultural dimension of what Apollo meant to the people who lived through it, and how the ending of Apollo affected the culture that had grown up around it. Apollo was not just a technical achievement, it was a cultural event of a specific and unusual kind. In July 1969, approximately 650 million people, roughly 1/5 of the world's population at the time, watched the Apollo 11 moon landing live on television. This was the largest shared real-time viewing event in human history to that point. The experience of watching a human being walk on the moon, of seeing in real time something that had been a dream for all of prior human history, was transformative for the people who lived through it. Not just as a pride in a national achievement, but as evidence of what human beings could do, what we were capable of, what was possible. This transformative quality of Apollo created an expectation. If we could go to the moon in 1969, with the technology of 1969, then surely by 1980 or 1990 we would be on Mars. Surely the moon would be a routine destination. Surely the science fiction future, space stations, lunar bases, interplanetary travel, was not just possible but imminent. The culture of the 1970s was saturated with this expectation. Science fiction became the dominant cultural genre for thinking about the future. Star Wars, Star Trek, 2001, A Space Odyssey. All of these reflected and amplified the expectation that space was the direction humanity was heading. When it became clear by the late 1970s and early 1980s that the expected future was not arriving, that the shuttle was expensive and limited, that Mars was not on any near-term horizon, that the moon was not going to be visited again in the foreseeable future, something happened to the culture. Not a dramatic collapse, not a sudden realization, but a gradual, uncomfortable recognition that the expectations generated by Apollo had not been met, and a slow adjustment to a world in which space was less central to how people imagined the future. The space shuttle, for all its engineering achievement, never had the cultural impact of Apollo. It was routine, or aspired to be routine, in a way that made it less compelling as a cultural object. The launches were newsworthy, but not the same kind of news. The shuttle missions were about science and technology and logistics, not about the singular human experience of standing on another world. The Challenger disaster in 1986 was a cultural shock. 7 astronauts died on live television in front of school children who had been brought to watch because one of the crew was a teacher. The disaster crystallized anxieties about the shuttle program that had been accumulating, about its costs, its risks, its failure to deliver the routine access to space that had been promised. After Challenger, the shuttle program was grounded for almost 3 years while the causes of the disaster were investigated and the vehicle was modified. The program returned to flight in 1988 and continued until the Columbia disaster in 2003, when another 7 astronauts died during re-entry due to damage to the shuttle's thermal protection system. 2 disasters, 14 deaths, a 30-year program that never achieved the flight rate or cost targets it had promised. And at the end of it, in 2011, no replacement vehicle ready to carry American astronauts to orbit. For 9 years after the shuttle's retirement in 2011, the United States had no capability to launch its own astronauts to space. American astronauts rode to the International Space Station on Russian Soyuz capsules, paying Russia approximately $90 million per seat. This is the trajectory of American human spaceflight after Apollo. not a steady progression toward greater capability, a complex, expensive, repeatedly tragic effort to maintain a minimal human spaceflight capability, while the more ambitious goals, moon base, Mars mission, sustainable expansion of human presence, remained perpetually deferred. Now let us think about what the moon actually represents as a destination for the coming decades, why returning to it matters, what it offers that is worth the enormous cost, and why the conversation about going back has regained urgency after decades of dormancy. The moon matters for several reasons that have become clearer since the Apollo era. First, water ice. The confirmed presence of water ice at the lunar poles changes the moon from a scientifically interesting but logistically difficult destination into a destination with local resources that can support sustained human operations. Water ice can provide water for drinking and agriculture. Electrolysis can split water into hydrogen and oxygen, providing rocket propellant and breathable atmosphere. A lunar base near the poles could be genuinely self-sufficient in ways that would not be possible if all supplies had to be launched from Earth. Second, the moon as a staging point for deep space. The moon is in a specific gravitational location relative to Earth that makes it a natural staging point for missions to other destinations in the solar system. Propellant produced on the moon from water ice can be used to top off spacecraft heading to Mars or the asteroid belt, dramatically reducing the mass that must be launched from Earth's deep gravity well. The delta V, the change in velocity required to reach Mars from lunar orbit, is substantially less than from Earth orbit, making lunar propellant a valuable resource for interplanetary exploration. Third, the moon as a scientific laboratory. The permanent darkness of the polar craters provides near absolute zero temperatures that are ideal for certain types of astronomical observation. A radio telescope on the moon's far side, permanently shielded from Earth's radio noise, would have access to long wavelength radio frequencies that are blocked by Earth's ionosphere, providing windows into the universe that are unavailable from Earth. The regolith of the lunar highlands records billions of years of solar activity and cosmic ray exposure that can be read like a geological record of the Sun's history. Fourth, the moon as a proving ground. Technologies required for Mars exploration, autonomous life support, in situ resource utilization, long-duration human habitation far from Earth, can be developed and tested on the moon at far less risk than on Mars. The moon is 3 days from Earth. Mars is 7 months. Emergencies that can be survived on the moon because help can arrive would be fatal on Mars because help cannot. These reasons are compelling. They argue not just for a return visit, but for sustained, long-term human presence on the moon as a step in the development of a spacefaring civilization. And yet they are also the arguments that have been made in various forms since the end of Apollo. The water ice was suspected before it was confirmed. The value of the moon as a staging point has been understood since the 1960s. The scientific opportunities have been advocated for by the lunar science community for decades. What has been missing is not the reasons. The reasons have always been there. What has been missing is the political, institutional, and economic structures required to convert compelling reasons into sustained action. Now those structures may finally be changing. SpaceX and the commercial space sector have introduced something that did not exist in the Apollo era: private companies with genuine technical capability and genuine financial incentive to develop lunar transportation. Blue Origin, Astrobotic, Intuitive Machines, iSpace, a range of companies are developing lunar landers, surface mobility systems, and communication relays that did not exist 5 years ago. In February 2024, Intuitive Machines landed its Nova C lander near the lunar South Pole, the first American spacecraft to successfully soft land on the moon since Apollo 17 in 1972. The lander tipped over upon landing due to surface conditions that were different from predictions, but it continued to operate and return data. It was the first commercial lunar landing ever achieved, and it was paid for by NASA under a commercial services contract rather than through the traditional cost-plus program model. This is a different model than anything that existed during Apollo. Commercial companies bearing the development risk and cost, competing for NASA contracts rather than operating as cost-plus contractors, with financial incentive to develop efficient and reusable systems. If this model succeeds at scale, if SpaceX's Starship achieves the cost reductions it is designed for, if commercial lunar landers become routine, if the economics of lunar operations improve dramatically, the question of why we never went back will become historical rather than contemporary. We will have gone back. Not under the same political circumstances that took us there the first time, not under the same economic model, not with the same institutional structures, but back. And the 50-year gap from Cernan's footsteps in 1972 to the footsteps of whoever is next to stand on the moon will be understood as a specific historical episode, a period when the political, institutional, and economic conditions for sustained human presence beyond Earth were absent. And the beginning of whatever comes after will be understood as the moment when those conditions finally, imperfectly, belatedly, began to come together. Now let us think about what the moon represents at the deepest level, not as a destination for astronauts, or a staging point for Mars missions, or a scientific laboratory, but as an object in the human sky, and what our relationship to it says about us. The moon has been part of the human experience for longer than our species has been anatomically modern. Our ancestors, Homo erectus, Homo heidelbergensis, the common ancestors of modern humans and Neanderthals, watched the moon rise and set for hundreds of thousands of years before we existed. The lunar cycle, 29.5 days from new moon to full moon to new moon again, has been woven into human timekeeping, agriculture, religion, and culture since before recorded history. Every human civilization has had a relationship to the moon. Every mythology includes it. Every calendar system has been organized around it. The word month is etymologically linked to the word moon. The month is the moon's cycle, the original unit of time longer than a day. When Apollo 11 landed on the moon in 1969, human beings set foot on an object that had been part of human consciousness since before consciousness existed in its current form. It was not just a scientific achievement, it was the completion of a relationship, the first physical contact with something that had been observed, worshipped, feared, and wondered about for the entirety of human existence. And then we left, and did not go back. The moon is still there. It rises and sets as it has always risen and set. The same tidal forces it has always exerted still pull the oceans and slow the Earth's rotation and maintain the axial tilt that gives us our seasons. The same light still falls on the same ancient surface. But now there is something different. Now we know what is there. Not just mythology and speculation, but measurements and samples and orbital data. We know the moon's age and its composition and its internal structure. We know it formed from the debris of a giant impact 4.5 billion years ago. We know it has water ice in its polar craters. We know its surface records billions of years of solar and cosmic history. And we have walked on it. 12 people have stood on the surface of the moon. They collected rocks and drove a rover and planted flags and left retroreflectors that laser pulses still bounce off today. They looked up at the Earth, a blue and white marble floating in the black void, and felt something that no previous human being had ever felt. And they came home, and no one has gone back. That fact, that specific 50-year absence, is one of the most significant facts about the civilization that produced the moon landing. We did the most ambitious thing any civilization has ever done, and then we stopped. Not permanently, not forever. The absence is ending, slowly, expensively, imperfectly, but ending. But the 50 years of absence are real. They represent decisions that were made, resources that were not committed, knowledge that was allowed to degrade, opportunities that were not taken. Understanding why they happened, honestly, without consolation, is part of understanding what kind of civilization we are, what we are capable of when conditions align, what we fail to sustain when they do not, what it takes to do something that was worth doing once and to make it worth doing again and again and again. The moon is waiting. It has always been waiting. What has changed is us. What we are capable of, what we know, what the economics of getting there look like, what the geopolitical pressures are, and whether the structures are, finally, belatedly, coming together to make sustained human presence there possible. That is the real reason we never went back. Not one reason, many. Not simple, complex. Not a failure of courage or vision, a failure, or a series of failures, of the institutional, political, and economic structures through which a civilization converts ambitions into sustained action. And the understanding of those failures is itself valuable. Because the moon is not the last destination, Mars is next. And after Mars, the asteroid belt, the outer planets, the nearest stars in the longest and most ambitious of futures. Every lesson from why we stopped going to the moon is a lesson for why we might stop going to Mars. And knowing those lessons, taking them seriously, is part of what it would take to not repeat them. Let us now think about something that the previous analysis has established, but not fully drawn out: the specific relationship between the cost structure of space exploration and the political will required to fund it. Because this relationship is the central mechanism through which all the other factors we have discussed operate. Every decision that ended or constrained a lunar program, the cancellation of Apollo 18, 19, and 20, the budget compromises that shaped the shuttle, the repeated deferrals of the lunar base, the decade-long development of SLS at enormous cost, was ultimately a decision about money, about how much a civilization was willing to pay, and what it was willing to pay for instead. This is not a criticism. It is a description of how democratic governments allocate resources. In a democracy, the government's budget reflects, with various distortions and delays, the collective priorities of the population. Space exploration competes with healthcare, education, infrastructure, defense, social programs, and all the other things that governments do. The fraction of the budget allocated to space exploration reflects, in some rough and imperfect way, how much the population values space exploration relative to everything else. In the 1960s, the fraction was approximately 4.4%. This was not a natural equilibrium, it was a wartime allocation, sustained by the perceived existential threat of Soviet supremacy in space and the direct connection between the rocket technology of space exploration and the missile technology of nuclear deterrence. When the perceived threat diminished, when the Soviet space program visibly stumbled after the N-1 failures, when the United States landed on the moon and won the race, the political case for wartime-level spending on space exploration collapsed. The budget reverted toward a peacetime allocation. The peacetime allocation, currently approximately 0.3% of the federal budget, is not enough to sustain the kind of program that reached the moon in 1969. It is enough to sustain the International Space Station, to conduct a range of robotic science missions, and to fund the development of a new heavy-lift rocket over a decade-plus timeline. It is not enough to build and sustain a permanent lunar base, or to mount a Mars mission on any ambitious timetable. The political economy of space exploration has not fundamentally changed since the end of Apollo. The budgets have fluctuated, up briefly during the George W. Bush Vision for Space Exploration period, down during the Obama administration, up again during the Trump administration with Artemis, relatively stable under Biden. But the underlying peacetime allocation has not returned to the Apollo-era fraction, and without a political shock comparable to Sputnik, it is unlikely to. This creates a specific challenge. The goals of sustainable lunar presence and eventual Mars exploration require investment levels that are above the peacetime allocation but below what was achieved during Apollo. They require something in between, a sustained, elevated commitment that is politically sustainable across multiple administrations and congressional cycles. This kind of sustained, elevated commitment is rare in American political history. It requires that the program be insulated from the cycle of presidential priorities that typically reorganizes major government initiatives every 4 to 8 years. The cycle that has derailed every post-Apollo space exploration initiative. The Artemis program is the current attempt to establish this kind of sustainable commitment. Its architecture has been designed, at least in part, with political durability in mind, using commercial partners rather than purely government contractors, spreading economic benefits across a wide range of congressional districts, and building an international coalition of partner nations through the Artemis Accords that creates external political pressure to continue. Whether this architecture is durable enough to survive the political cycles that ended every previous post-Apollo program is not yet known. Now let us think about something that is rarely discussed in the context of the Moon program: the role of Congress, specifically in shaping the decisions that led to the 50-year gap. Presidential administrations propose space programs. Congress funds them, or does not fund them. The interaction between presidential priorities and congressional appropriations has been the mechanism through which every post-Apollo program has been distorted, delayed, or cancelled. The Nixon administration, beginning in 1969, was immediately faced with the budget pressure of the Vietnam War and the domestic spending demands of the Great Society programs. Nixon's instinct was to cut the NASA budget substantially. The Apollo program had achieved its political goal, and the enormous expenditure was no longer justified by the perceived threat. But NASA had political advocates in Congress, particularly in the states where NASA centers were located: Texas, Florida, Alabama, Ohio. The states with major NASA facilities had senators and representatives whose constituencies depended on NASA spending and who fought to protect it. The result was a negotiated outcome that preserved NASA's budget at a level above what Nixon wanted, but below what would have been needed to sustain the full post-Apollo program envisioned in the 1969 planning. The lunar base was deferred. Apollo was shortened. The shuttle was funded as a compromise between what NASA wanted and what the budget would support. This pattern, congressional protection of NASA facilities and jobs at the expense of coherent programmatic priorities, has repeated throughout the post-Apollo period. The Space Launch System is, in many ways, a product of this pattern. When the Constellation program, the previous attempt to develop a heavy-lift rocket for lunar and Mars exploration, was cancelled by the Obama administration in 2010, Congress responded by directing NASA to develop a replacement, providing specific design requirements that ensured the new rocket would be built using the same contractors and facilities as the cancelled Constellation program. SLS was explicitly designed in law to use existing shuttle infrastructure, the Michoud Assembly Facility in Louisiana for the core stage, Aerojet Rocketdyne's facilities in Mississippi and Alabama for the engines, the Vehicle Assembly Building at Kennedy Space Center for integration. These facilities employed tens of thousands of people in politically important states. Their congressmen ensured that the law directing SLS development protected those jobs. The result is a rocket that is significantly more expensive than it would have been if designed purely on technical merit, because it is designed to use expensive, politically protected facilities and suppliers rather than the most cost-effective alternatives. SpaceX's Starship, by contrast, was designed without those political constraints. It uses SpaceX's own manufacturing facilities in Boca Chica, Texas. It uses engines designed and built in-house. It is optimized for cost efficiency and reusability rather than for political distribution of economic benefits. The cost difference, SLS at approximately $4 billion per launch versus Starship at potentially tens of millions of dollars per launch if full reuse is achieved, reflects this difference in design philosophy and political constraint. The political economy that produced SLS also produced the 50-year gap. The same mechanisms that protect NASA jobs and facilities in politically important states also prevent the development of the most cost-effective approaches to space transportation. The congressional oversight that ensures NASA spending is distributed across many districts also ensures that the spending is less efficient than it could be. This is not corruption in the simple sense. It is the normal operation of democratic political economy in the presence of concentrated benefits and diffuse costs. The workers at Michoud and Stennis and Aerojet's facilities have strong incentives to protect their jobs through congressional representation. The American taxpayers who pay for SLS at $4 billion per launch have diffuse incentives. No individual taxpayer pays enough of the cost to justify spending significant effort lobbying against it. The result is a persistent gap between what would be technically and economically optimal and what the political economy produces. Understanding this mechanism is essential for understanding why we never went back to the moon. It was not primarily a failure of technical capability. The technical capability existed in the early 1970s to continue lunar exploration and has been rebuilt in various forms since then. It was a failure of political economy. The mechanisms through which democratic societies make and sustain collective investment decisions proved inadequate to the challenge of sustaining the most ambitious exploration program in human history. Now let us think about something more concrete. The specific missions that were cancelled, what they would have found, and what we have missed by not having that knowledge. Apollo 18 was planned to land in the Schroeter's Valley region, a large, sinuous rill likely formed by ancient lava flows that would have provided access to subsurface rock layers not available at any previous landing site. The scientific targets were chosen to study the volcanic history of the Moon and the nature of the mantle rocks exposed by erosion of the rill walls. Apollo 19 was planned for the Hyginus Rill region, another volcanic feature with potential access to the deep crust. The mission would have deployed a long-range rover capable of travelling much farther from the landing site than previous missions, potentially covering 100 kilometres or more. Apollo 20 was planned for Tycho crater, one of the youngest and deepest large impact craters on the Moon, with a central peak that would have provided access to rocks from deep within the lunar crust. Tycho's relative youth, approximately 108 million years, would have made it scientifically distinct from the much older sites visited by previous missions. All three missions were cancelled in 1970. The scientific understanding that would have been gained of the Moon's volcanic history, its deep crustal structure, the nature of young impact craters, has not been recovered. The samples that would have been returned from Tycho and the sinuous rills have never been analysed. The hypotheses that those missions would have tested or refuted are still hypotheses. This is a specific scientific loss that is measurable in terms of what we do not know about the Moon. It is not abstract, it is the specific absence of knowledge that would have changed our understanding of lunar and solar system history. Beyond the cancelled Apollo missions, there were planned subsequent programs that were never developed. The Apollo Applications Program, AAP, was a plan to use surplus Apollo hardware for extended lunar and Earth orbital missions. It produced Skylab, the space station built from a modified Saturn V third stage that hosted 3 crews in 1973 and 1974. But the more ambitious AAP missions, including extended lunar surface operations with mobile laboratories and permanent base construction, were cancelled before they began. The Lunar Receiving Laboratory in Houston, the facility where Apollo samples were processed and curated, was designed with the expectation that hundreds of kilograms of samples would arrive over many years of future missions. It received 382 kilograms from 6 missions, and then received nothing more for 5 decades. The scientific infrastructure that was built for an ongoing lunar program sat largely idle, waiting for samples that did not come. Now, let us think about what has been discovered about the Moon since Apollo that would have been discovered decades earlier with a sustained program, because the timeline of discovery illuminates the cost of the gap. Water ice at the lunar poles was suspected from the 1970s onward. Theoretical calculations predicted that permanently shadowed craters near the poles would be cold enough to trap water molecules delivered by cometary impacts over billions of years. The confirmation came in 1994 with the Clementine mission, and more definitively in 2009 with LCROSS. If the lunar base planned in 1969 had been built in the 1980s, the water ice would almost certainly have been discovered and confirmed in the 1980s. The scientific understanding of the Moon's volatile inventory would be 30 to 40 years more advanced. The technology for extracting and using that water ice would be developed rather than being in its infancy. The Lunar Reconnaissance Orbiter, launched in 2009, has produced a comprehensive map of the lunar surface at resolutions of 0.5 meters per pixel, good enough to see the Apollo landing sites and the equipment left behind. It has characterized the topography of the polar craters in detail, identified potential landing sites for future missions, and measured the radiation environment that future astronauts will face. This information would have been enormously valuable for planning the lunar base if it had been available in the 1980s. Instead, it became available 40 years after it would have been needed for the program that was cancelled. The Lunar Crater Observation and Sensing Satellite, LCROSS, which confirmed water ice at the South Pole in 2009, was a small, relatively inexpensive mission that could have been flown decades earlier if it had been prioritized. The confirmation of water ice at the poles changed the calculus of lunar exploration. It established that the Moon has the resources needed to support sustained human presence. That knowledge, available since 2009, would have been transformative if it had been available in 1975. Each of these discoveries represents knowledge that could have shaped decisions about lunar exploration decades earlier if the sustained program had continued. Each delay in obtaining the knowledge is a delay in the development of the understanding needed to make good decisions about lunar exploration. The gap is not just a gap in human presence on the Moon, it is a gap in the accumulation of knowledge about the Moon, and about our own ability to extend human presence beyond Earth, that has constrained every subsequent decision. Now let us think about the specific contribution of the international dimension, the roles of the European Space Agency, Japan, India, and other space agencies in the evolving landscape of lunar exploration, because the Moon is no longer a two-party competition between the United States and the Soviet Union. The European Space Agency has contributed technology and expertise to multiple lunar exploration programs. ESA is a partner in the Artemis program, providing the service module for the Orion spacecraft, the propulsion and life support system that keeps the capsule operational between Earth and Moon. ESA's contribution is both technical and political. It ties European interests to the success of Artemis and creates a broader international coalition with a stake in the program. Japan's JAXA has conducted lunar orbital missions and is a partner in the Artemis program, with agreements for Japanese astronauts to participate in lunar surface missions. The SLIM mission, Smart Lander for Investigating Moon, landed near the lunar South Pole in January 2024, becoming the 5th country to successfully land on the Moon. The landing was precise to within 100 meters of the target, a demonstration of pinpoint landing technology that will be essential for landing near the scientifically and operationally valuable polar sites. India's ISRO conducted the Chandrayaan-3 mission, which successfully landed near the lunar South Pole in August 2023, the first successful lunar landing since 2020, and the first successful landing near the South Pole ever. The Chandrayaan-3 rover confirmed the presence of sulfur and other elements in the South Polar regolith, and the lander measured the temperature gradient in the soil. India became the 4th country to successfully land on the Moon, and the first to land near the South Pole. These are not trivial achievements. They demonstrate that the technical capability for lunar operations is spreading beyond the original two superpowers, creating a more diverse ecosystem of lunar exploration with different national interests, different technical approaches, and different risk tolerances. This diversification of the lunar exploration landscape is one of the most significant changes from the Apollo era. In 1969, 2 countries were competing for the Moon. In 2025, a dozen countries have lunar programs or aspirations, and commercial companies from multiple countries are developing lunar landers and surface systems. The competition is not just between the United States and China, though that bilateral competition is the most politically significant. It is a multilateral situation in which different countries and companies are pursuing different objectives with different architectures, and in which the norms and rules of behavior on and around the Moon are still being negotiated. The Artemis Accords, currently signed by more than 40 countries, represent one attempt to establish those norms. The International Lunar Research Station that China and Russia are developing represents a different set of norms. The gap between these frameworks, and the absence of any binding international authority to adjudicate disputes, creates real uncertainty about how conflicts over resources and locations on the Moon will be resolved. This is the governance challenge of the Moon, not just how to get there and what to do when you arrive, but how to manage a world that is simultaneously claimed by no one and coveted by everyone. Now let us think about something that cuts across all the specific technical, political, and economic factors we have discussed. The deep structural challenge of doing something very hard over a very long time. The Moon landing was achieved in a specific historical context that combined several conditions that are rarely all present simultaneously. A clear and specific goal, a hard deadline, existential political stakes, virtually unlimited resources by peacetime standards, an institutional culture that had been built from scratch and was not yet encrusted with the bureaucratic habits that develop in mature organizations. After Apollo, none of these conditions were simultaneously present. The political stakes were reduced when the Soviets lost the race. The resources were cut when the political stakes were reduced. The institutional culture calcified as NASA became a mature bureaucracy with established procedures, protected programs, and risk-averse decision-making. The goals became vague as the specific target was achieved, and no comparably specific successor goal was established with comparable political force. Sustaining the capabilities developed for Apollo over 50 years, maintaining the knowledge, the infrastructure, the industrial base, the institutional culture, would have required a sustained peacetime commitment of a kind that no democracy has ever made to a single technological program. The Roman Pantheon has stood for 2,000 years because stone buildings once built do not require continuous reinvestment to maintain. A space program requires continuous reinvestment in people, in infrastructure, in technology development, in institutional knowledge. And without that investment, it degrades. The American space program has degraded since Apollo. Not collapsed, NASA continues to do remarkable science and has maintained a human spaceflight capability in low Earth orbit throughout this period. But the specific capability to send humans beyond low Earth orbit, to the Moon, to Mars, to deep space, was allowed to lapse. The Saturn V production line was shut down. The engineers who built it retired. The institutional knowledge of how to design, build, and operate missions to the Moon was partially lost. The industrial base that supported Apollo was reorganized around other priorities. Building those capabilities back has taken decades and enormous resources, and the rebuilt capabilities, SLS and Orion, are less capable and more expensive than what existed in 1972. This is what the 50-year gap actually cost. Not just the specific missions that were not flown, not just the scientific knowledge that was not gained, not just the technological development that did not happen. The cost was also the degradation of capability itself, the loss of knowledge and experience and institutional culture that would have been the foundation for everything that came after. We are rebuilding that foundation now, imperfectly, expensively, with commercial partners and new approaches that did not exist in 1972, but rebuilding from a position of partial knowledge loss rather than continuous development. Now let us think about what would have been different, specifically and concretely, if the lunar program had continued without interruption from 1972 to the present. In this alternate timeline, the lunar base, planned in 1969, begins construction in the late 1970s. The base is located at one of the permanently illuminated peaks near the lunar South Pole, locations with near-constant sunlight for solar power, and within short range of permanently shadowed craters containing water ice. By 1985, the base supports a permanent crew of 6 to 12 researchers rotating on 6-month tours. The water ice in the polar craters has been confirmed and extraction technology has been developed. The base produces its own water and oxygen from lunar resources. By 1990, the base has expanded to support 20 to 30 people. It has conducted comprehensive geological surveys of the South Polar region, returning hundreds of kilograms of samples from diverse locations. It has deployed a radio telescope on the far side of the Moon, shielded from Earth's radio noise, that is conducting observations at frequencies impossible from Earth. By 2000, the lunar base is an established scientific and operational facility. It has developed the technology for large-scale water ice extraction and propellant production. It is serving as a staging point for missions to near-Earth asteroids. The cost of operating the base has decreased significantly as local resource utilization reduces the need to launch consumables from Earth. By 2010, a crewed Mars mission is launched using propellant produced on the Moon. The mission uses lunar-produced propellant topped off in lunar orbit, reducing the mass that must be launched from Earth by a factor of several. By 2025, there is a permanent human presence on both the Moon and Mars. This alternate timeline is speculative. It assumes that the technical development would have proceeded roughly as planned, and history shows that ambitious technical programs routinely encounter unforeseen challenges that delay and complicate their execution. The actual development would have been messier than this sketch, but the direction is what matters. Continuous investment in human presence on the Moon would have produced, over 50 years, a fundamentally different level of capability and knowledge than we have today. The Moon would be an operational environment rather than a destination we are preparing to visit again for the first time. The specific knowledge lost, the geological surveys, the resource mapping, the technology development, the accumulated operational experience, cannot be precisely quantified, but it is real, and its absence has consequences for everything we are trying to do now. Now let us think about where we actually are, what the realistic picture of the next decade of lunar exploration looks like, stripped of optimism and pessimism both. Artemis II will carry 4 astronauts around the Moon in 2025 or 2026. This is a significant step, the first humans to leave Earth orbit since Apollo 17 in 1972. The mission does not land, but it demonstrates the end-to-end capability of the SLS Orion system and gives astronauts their first direct experience of deep space. Artemis III will attempt to land near the lunar South Pole in 2026 or later. The landing uses SpaceX's Starship lunar lander, the human landing system, which must complete several technical milestones before it is ready to carry crew. The integration of SpaceX's commercial lander with NASA's government-developed Orion spacecraft is a new kind of mission architecture with its own technical and organizational challenges. If Artemis III lands successfully, it will be the first human presence on the Moon since 1972. The astronauts will spend a few days on the surface, collecting samples and deploying instruments. They will then return to the Orion spacecraft and come home. The missions after Artemis III, Artemis IV and beyond are planned to begin establishing the Lunar Gateway, a small space station in lunar orbit that will serve as a staging point for subsequent surface missions. The Gateway is an international project with contributions from ESA, Japan, Canada, and other partners. The lunar base that was planned in 1969 and cancelled in 1970 has been proposed again under the name Artemis Base Camp. It is planned for construction beginning in the late 2020s or 2030s at a location near the Shackleton crater rim at the South Pole, where near-constant sunlight provides power and nearby permanently shadowed regions contain water ice. Whether Artemis Base Camp is actually built depends on budget decisions that have not yet been made, on the technical success of missions that have not yet flown, and on political continuity that cannot be guaranteed. But the direction is clearer than it has been at any point since 1972. The South Pole as a destination, with its water ice and its near-constant sunlight, has replaced the equatorial landing zones of Apollo as the focus of human lunar exploration planning. The commercial partners who will provide critical components of the surface systems are more capable than they were 5 years ago. The international coalition supporting the program is broader than the Apollo-era bilateral competition. And in the background, SpaceX's Starship development continues. If Starship achieves its full operational capability, full and rapid reusability, 100-ton payloads to lunar orbit, costs per kilogram that are orders of magnitude below SLS, the economics of lunar exploration will change fundamentally. The Moon will become accessible not just to national space agencies, but to a wider range of actors. The question of whether we will sustain a continuous human presence on the Moon, whether this time, unlike after Apollo, we will keep going, depends on factors that are still unresolved. Budget sustainability, political continuity across administrations, technical success of the systems being developed, commercial viability of lunar operations, the emergence of the lunar economy that advocates have long predicted. All of these factors are in play, none of them are guaranteed. But the combination of renewed government investment in the Artemis program, commercial development of lunar transportation by SpaceX and others, international partnerships that spread the cost and the political investment, and the confirmed presence of water ice that provides a local resource base, this combination is more favourable than anything that has existed since Apollo. The 50-year gap may be ending. The real reasons it lasted as long as it did, the collapse of the political conditions that created Apollo, the failure to sustain institutional knowledge, the perverse incentives of cost-plus contracting, the inability to maintain a peacetime commitment to a goal that required wartime resources, and the fundamental difficulty of sustaining the most ambitious thing a civilization has ever done, are not fully resolved. But they are being addressed, imperfectly and partially, by a combination of commercial innovation and renewed political attention that did not exist during the long gap. What we do with this moment, whether we sustain the commitment and build on it, or allow the same forces that ended Apollo to erode the Artemis program, will determine whether the 50-year gap is a historical episode or a pattern. The Moon is waiting. It has waited since December 14th, 1972. What comes next is our choice. Let us now think about something that the previous analysis has circled but not directly addressed. The question of what it actually felt like from the inside to be part of the Apollo program and then to watch it end. Because the history of why we never went back is not just institutional and political, it is also personal. It is the history of specific human beings who devoted their careers and in some cases their lives to something extraordinary, who watched it end and who spent the following decades in various relationships to that ending. Some of them trying to rebuild what was lost, some of them moving on, some of them never fully reconciling with what happened. The engineers and managers at NASA who were there during Apollo describe a specific quality of experience that is hard to capture in institutional histories. It was not just a job, it was a mission in the fullest sense, a collective enterprise of such magnitude and such urgency that it absorbed everything. People worked extraordinary hours, not because they were required to, but because they wanted to. The goal was clear, the deadline was real, the stakes were understood, and the community of people working toward it had a shared identity that was unlike anything they had experienced before or would experience again. George Mueller, the NASA Associate Administrator for manned spaceflight during Apollo, later said that the loss of the Saturn V production line was the worst decision in the history of the American space program. He understood at the time that once the line was shut down, the knowledge would be lost. He fought against the decision. He lost. The engineers who were told to dismantle the production line, who were told to take apart the infrastructure they had spent years building, described it as a kind of institutional mourning. Not just the end of a program, but the destruction of something that had taken years to create and that they knew could not easily be rebuilt. Rocco Petrone, who directed the Apollo program at the Kennedy Space Center during the moon landings, later said that when the last Saturn V was rolled out and the production line was shut down, he felt as though something irreplaceable had been lost. Not just the hardware, the knowledge, the culture, the community of people who knew how to do something that no one had ever done before. This personal dimension of the loss is relevant because it explains something that is otherwise puzzling: why the institutional knowledge degraded so rapidly. The degradation was not just because documentation was incomplete. It was because the people who carried the tacit knowledge, the experienced engineers, the skilled machinists, the test engineers who knew from accumulated experience what would work and what would fail, dispersed when the program ended. They went to other jobs, other programs, other companies, or they retired. The community that had built and sustained the knowledge dissolved. Reconstituting that community 50 years later is not just a matter of reading old documents. It requires relearning through experience what was originally learned through experience. This is inherently slow and expensive, which is why the development of SLS and Orion has taken so much longer and cost so much more than Apollo, even with the enormous advantage of modern computing, materials science, and manufacturing technology. Now let us think about the astronauts specifically, the 12 men who walked on the moon, and what their subsequent lives say about the nature of what they experienced. Walking on the moon is, by any measure, one of the most unusual experiences a human being can have. You are standing on another world. The Earth hangs in the black sky above you, 4 times the size of the moon as seen from Earth, blue and white, and obviously fragile. Under your feet is ground that has not been disturbed for billions of years. Around you is silence. Not the silence of an empty room, but the silence of a world without atmosphere, where no sound can propagate, where the only sounds you hear are the ones transmitted through your suit's microphone or through contact with the surface. The 12 men who had this experience were changed by it in ways that they spent years trying to articulate. Their descriptions are remarkably consistent and remarkably different from what you might expect. The most common description is not triumph or pride or the exhilaration of achievement. It is perspective, a shift in the sense of what matters, a recognition, visceral and lasting, of the smallness of human conflicts and the preciousness of the Earth when seen from outside it. Edgar Mitchell, after returning from Apollo 14, experienced what he described as an epiphany, a sudden, overwhelming sense of the interconnectedness of everything, of the universe as alive and conscious in a way that he had never felt before. He spent the rest of his life exploring this experience, founding the Institute of Noetic Sciences to study consciousness and its relationship to the physical world. Buzz Aldrin, after Apollo 11, struggled with depression and alcoholism in the years following the moon landing. He has been frank about the difficulty of returning from something that nothing in subsequent life could match. The question of what do you do after walking on the moon is not a trivial one. The achievement was so extraordinary that ordinary life felt diminished by comparison. James Irwin, who walked on the moon during Apollo 15, returned with a deepened religious faith and spent the rest of his life on religious mission work. He described the moon as a place that made him feel the presence of God more directly than anything else he had experienced. Alan Bean, who walked on the moon during Apollo 12, became a painter after leaving NASA and devoted the rest of his career to painting scenes from the Apollo program, trying to capture in visual art what photographs could not fully convey. He used actual lunar dust in his paints, mixing it into the pigments so that the moon itself was part of the artwork. Charlie Duke, who walked on the moon during Apollo 16, has described the experience as so overwhelming that it contributed to emotional difficulties in his marriage and family life in the years following. He later found resolution through religious conversion. These are not the stories of men who achieved something and moved comfortably on to other achievements. They are the stories of people who had an experience so far outside the range of ordinary human experience that they spent the rest of their lives in various forms of processing it, integrating it, sharing it, searching for meaning in it. This tells us something about the nature of what was achieved with Apollo. It was not just a technical accomplishment, it was an experience, a qualitatively new kind of human experience that changed the people who had it in deep and lasting ways. And it was experienced by 12 people. In the half-century since, no additional human being has had it. This is a kind of impoverishment that the technical and political analysis does not fully capture. The experience of standing on another world is real, and it is valuable, and we have chosen, through a series of political and economic decisions, to keep it confined to 12 people who are now all in their 80s or 90s. The astronauts who trained for missions that were cancelled, the astronauts selected for Apollo 18, 19 and 20, who never flew to the moon, carry a specific kind of loss. Jack Schmitt, who flew on Apollo 17 as the only professional geologist to walk on the moon, has spent the decade since Apollo advocating for a return to the moon and expressing frustration at the decisions that have delayed it. He understands, in a way that few others do, what remains to be learned from the moon and what it cost to abandon the program before that learning was complete. Now let us think about something that is more philosophical, the question of what it means for a civilization to do something extraordinary once and then stop. History offers a few analogies, and they are instructive. The voyages of Zheng He, the Chinese admiral who commanded a fleet of massive treasure ships to Southeast Asia, South Asia, Arabia and East Africa in the early 15th century, represent perhaps the most striking historical parallel. Zheng He's fleet included vessels that were, by some estimates, 5 times the size of the ships Columbus would sail 60 years later. The Chinese had the most advanced naval technology in the world. They reached the African coast and could have continued to Europe or to the Americas. And then the Yongle Emperor, who sponsored the voyages, died. His successor, the Xuande Emperor, ordered the voyages stopped. The shipyards were closed. The records of the voyages were deliberately destroyed. The great ships were left to rot. Within a generation, China's extraordinary naval capability was gone. The knowledge of how to build the treasure ships was lost. When Chinese historians looked back centuries later, they found only fragments of evidence that the voyages had occurred, evidence that some scholars initially dismissed as exaggeration. The parallel to Apollo is not perfect. The political context was different. The reasons for stopping were different. The subsequent history was different. But the core dynamic is the same: an extraordinary achievement in exploration, followed by a deliberate decision to stop, followed by the degradation of the capability to repeat it. And in the Chinese case, as in the American case, the stopping was not the end of history. The world continued, China continued, but the specific capability that had been developed and the specific knowledge embedded in that capability was lost. And what followed was shaped by that loss in ways that were not recognized until much later. The European civilizations that came after Zheng He, that sailed to the Americas and Africa and Asia and eventually around the world, did so without the benefit of the Chinese navigational and shipbuilding knowledge that could have made their task easier and safer. They had to learn everything themselves from the beginning at the cost of enormous effort and enormous loss of life. We are, in some sense, relearning everything about how to go to the moon. Not from scratch. Too much knowledge survived in various forms for that to be accurate, but relearning in the sense of having to rebuild capabilities that once existed at enormous cost, when continuous development would have produced those capabilities at a fraction of the cost and with the accumulated knowledge of decades of operational experience. Now let us think about the geopolitical dimension more carefully, because the comparison to Zheng He's voyages includes another parallel that is specifically relevant to our current situation. After China stopped the treasure ship voyages, the world did not stop. Other civilizations continued to explore. Portugal sailed around Africa. Spain reached the Americas. Eventually, European ships arrived in Chinese waters and changed the balance of power in ways that China had no basis to anticipate, having withdrawn from the maritime world. The analogy to the current situation. After the United States stopped the Apollo program, the world did not stop. Other nations continued to develop space capabilities. The Soviet Union continued its robotic and crewed programs. China began its space program. Europe, Japan, India developed their own capabilities. And now, half a century later, China is approaching the moon with capabilities that did not exist when the United States last walked there. The geopolitical balance of the coming century may be partly determined by who establishes a lasting presence at the moon's south pole, who controls the water ice, who builds the infrastructure, who shapes the norms of behavior on a world that will become increasingly important. The United States, having dominated the first era of lunar exploration, is not guaranteed to dominate the second. The 50-year gap has created space, literally and figuratively, for other actors to develop capabilities, build programs, and establish presences that did not exist when Apollo ended. Whether this competition produces conflict or cooperation, whether it leads to the establishment of agreed international frameworks for managing lunar resources and activities, or to a repetition of the unmanaged competition over Antarctic territory that the Antarctic Treaty System eventually regulated, is one of the most important open questions in space policy. The decisions being made now about Artemis, about commercial lunar transportation, about the Artemis Accords, about the US-China relationship in space, are shaping the trajectory of that competition in ways that will have consequences for decades. Now let us think about what the moon landing means at the deepest level for what humanity can become. The moon landing is the most extraordinary thing our civilization has ever done. Not in terms of scientific knowledge gained, though the knowledge gained was significant. Not in terms of strategic advantage, though the strategic motivation was central. But in terms of what it demonstrated about what human beings are capable of when they commit sufficient resources and sufficient intelligence and sufficient will to a difficult problem. The problem of getting to the moon was genuinely hard. It was hard in ways that were not fully understood at the outset. It required the development of new materials, new manufacturing processes, new computing approaches, new human physiological understanding, new organizational methods. It required solving problems that had never been solved before, under time pressure, with the consequences of failure being either death or national humiliation. And it was done. 12 people walked on the moon. They came home. The program succeeded. This is not trivial. The success of Apollo is evidence that human civilization is capable of sustained, coordinated effort at extraordinary scale. That when the conditions are right, we can do things that seem impossible until they are done. The failure to sustain the program after the initial success is also evidence about the limits of those conditions, about how difficult it is to maintain the motivation and the resources and the institutional coherence required for the most ambitious kinds of human enterprise. Understanding both pieces of evidence, the extraordinary success and the subsequent failure to sustain it, is essential for thinking clearly about what comes next. The next steps, a return to the moon, a permanent lunar presence, eventually a crewed Mars mission, are comparably difficult to Apollo in some respects and different in important ways. They are different in that we are not starting from zero. The knowledge base is vastly larger. The computational tools are enormously more powerful. The materials science has advanced dramatically. The understanding of human physiology in space is 50 years more developed. The commercial sector has capabilities it did not have in 1969. The international coalition is broader. They are similarly difficult in that the fundamental challenges have not gone away. Getting human beings to the moon still requires enormous amounts of energy and precise technology. Sustaining them there still requires solved problems of life support and radiation protection and psychological well-being. Returning them safely still requires systems that work every time without exception. And they are more difficult in one specific way. The political conditions that sustained Apollo, the perceived existential threat of Soviet supremacy in space, the wartime level budget allocations, the existential stakes attached to the specific goal, have not been recreated and may not be recreatable in the same form. What has potentially emerged in their place is a different set of conditions: the commercial economics of SpaceX and other companies, which create financial incentives for cost reduction that did not exist in the Apollo era. The confirmed presence of water ice at the poles, which creates a practical resource base that makes sustained lunar operations economically viable in a way they were not in 1972. And the international competition with China, which is creating political urgency even if it is not producing Apollo-level budget commitments. Whether these conditions are sufficient to sustain a program through the decades required to establish a permanent lunar presence, or whether they will prove, like the conditions of the post-Apollo period, to be inadequate to the challenge, is the central open question of the current moment in space exploration. Now let us think about something that connects the Moon specifically to the longest arc of human history and human possibility. The Moon is approximately 4.5 billion years old. It formed from the debris of a giant impact between the early Earth and a Mars-sized protoplanet named, by convention, Theia. The violence of that impact, energy equivalent to trillions of nuclear weapons, a collision that would have melted significant portions of both bodies, produced the Moon and simultaneously contributed to Earth's development in ways that may have been essential to the emergence of life. The Moon's gravitational pull stabilizes Earth's axial tilt. Without the Moon, Earth's axial tilt would vary chaotically over millions of years, producing climate swings far more severe than anything our planet has experienced in its geological history. Whether life could have developed to its current complexity on an Earth without the Moon's stabilizing influence is uncertain, but the question is serious. The Moon's tidal forces have been slowing Earth's rotation for 4.5 billion years. When the Moon formed, Earth's day was approximately 6 hours long. Over the subsequent billions of years, lunar tidal friction has slowed the rotation to the current 24 hours. The Moon itself has been moving away from Earth at approximately 3.8 centimeters per year, as Earth's rotational energy is transferred to lunar orbital energy. The Moon has shaped the chemistry of Earth's oceans through its tidal mixing. It may have played a role in the origin of life by creating the tidal zones, areas that are alternately covered and exposed by tides, where the concentration and drying of organic molecules might have facilitated the first self-replicating chemistry. We live on a planet whose character has been fundamentally shaped by the Moon. The Moon is not a separate world that we might visit occasionally. It is a companion that has been influencing Earth's evolution for as long as Earth has been Earth. Understanding this relationship fully requires visiting the Moon repeatedly with different instruments at different times, examining different aspects of its geology and chemistry and physics. The 6 Apollo landings gave us the first fragments of this understanding. The full understanding requires decades or centuries of systematic exploration. And eventually, in the longest arc of the story, the Moon's resources may be essential to the expansion of human civilization beyond Earth. The water ice. The helium-3 in the regolith, potentially valuable as fusion fuel. The near-vacuum environment, ideal for certain manufacturing processes. The near-constant sunlight at the poles, available for solar power. The extreme cold of the polar craters, useful for scientific instruments. The Moon is not a dead world. It is a world that has been waiting for 4.5 billion years for the intelligence that evolved on the planet next door to come and understand it, and eventually to use it as the first stepping stone in the expansion that may eventually take that intelligence to other stars. Whether that expansion happens, whether the Moon becomes the first of many stepping stones, or remains a destination visited occasionally and briefly, depends on decisions that are being made now, in this specific historical moment by people who may not fully understand the magnitude of what they are deciding. The 12 people who walked on the moon left footprints that will last for millions of years. There is no wind or water on the moon to erode them. Those footprints are still there. They will still be there long after the Apollo astronauts are gone, long after the civilization that made them is unrecognizable, long after the specific political context that produced them is forgotten. They are evidence, preserved for geological time, that something extraordinary happened here, that a species that evolved on a small planet around an ordinary star developed the intelligence and the will to cross the void between worlds and stand on the surface of another. It happened once, and then it stopped for 50 years. What happens next is still being decided. Go outside tonight, look up, find the moon. You almost certainly can. The moon is the brightest object in the night sky after the sun. It has been there every night since before your species existed. It has been there longer than there were eyes to see it. Look at it, not as a metaphor, as a physical object, a sphere of rock 3,474 kilometers in diameter, 384,400 kilometers away, reflecting sunlight back at you across the void. Formed 4.5 billion years ago from the debris of a collision so violent it partially melted the early Earth. Old enough that the oldest rocks on its surface predate complex life on Earth by more than 1 billion years. Now think about what is on its surface. The footprints are still there. 6 landing sites, all clustered in the equatorial regions of the near side. 12 sets of footprints in the lunar regolith, the fine powder that blankets the surface to depths of meters, undisturbed since it was formed by billions of years of micrometeorite impacts. No wind, no water, no geological activity to erase them. Those footprints will outlast every building humanity has ever constructed, every institution, every nation, every civilization. They will still be there in 1 million years, in 10 million years. They are among the most durable artifacts our species has ever made. And we made them between 1969 and 1972. And then we stopped. The last person to touch the lunar surface did so on December 14th, 1972. Eugene Cernan climbed the ladder of the lunar module, paused at the top and said, knowing he was about to become the last person on the moon, at least for a long time, words he had prepared for the moment. We leave as we came, and, God willing, as we shall return, with peace and hope for all mankind. He climbed inside, the hatch closed, the engine fired, and for more than 50 years the moon has been exactly as he left it, exactly as they all left it. The footprints, the abandoned equipment, the flag almost certainly bleached white by 50 years of solar ultraviolet radiation, the retroreflectors that laser pulses still bounce off today, the one piece of Apollo hardware that is still being actively used, still returning data, still measuring the moon's distance from Earth to millimeter precision. 12 people walked there. 12. In the entire history of our species, 12 people have ever stood on another world. And now think about what we have been talking about tonight. Why did we stop? The real answer is not simple, and it is not comfortable. It is not a story of one bad decision or one failure of leadership or one budget cut. It is a story about what it takes to sustain the most ambitious thing a civilization has ever done, and about the gap between what that requires and what the political, economic, and institutional structures of a democratic society can reliably provide. Apollo was built on a foundation that was simultaneously extraordinary and precarious. Extraordinary because it actually worked, because 12 people walked on the moon, which is not something that could have been predicted with confidence when Kennedy announced the goal in 1961. Precarious because the foundation was political and economic conditions that were specific to a particular historical moment and that began to erode as soon as the goal was achieved. The existential competition with the Soviet Union that created the budget, the specific political genius of Kennedy's goal, bounded, specific, urgent. The industrial capacity built for military rockets that was redirected to moon rockets. The institutional culture of a new agency not yet calcified by bureaucratic habits. The community of engineers and scientists who had not yet been told it was time to stop. All of these conditions aligned in the 1960s. None of them were guaranteed to persist. And they did not persist. The Soviet program faltered. The budget was cut. The Saturn V production line was shut down while men were still walking on the moon. Apollo 18, 19 and 20 were cancelled. The lunar base that was planned in 1969 was never built. The engineers retired. The knowledge degraded. The institutional memory of how to do this, embedded in the people who had done it, dispersed. And for 50 years, the moon waited. It waited through the shuttle program, 30 years of low Earth orbit, of an extraordinary vehicle that never delivered on its promise of routine, cheap access to space, that killed 14 people in 2 disasters, that ended in 2011 without a replacement ready. It waited through the Space Station Freedom program that became the International Space Station after the Soviet Union collapsed and Russia became a partner instead of a competitor. It waited through the Constellation program that was cancelled before it flew. It waited through the Vision for Space Exploration that produced a great deal of planning and not much flight. And now, for the first time since 1972, we are going back. Not yet, but soon. Artemis 1 flew in 2022. Artemis 2 will carry humans around the moon. Artemis 3 will land. Whoever steps off that lander and stands on the lunar surface will be standing in the footsteps of 12 men who went there half a century ago. They will be returning to a place their species visited and then abandoned. They will be the first to touch the moon in a period longer than many of them have been alive. Think about what that means. The 50-year gap is not just a gap in missions, it is a gap in human experience. Every person now alive on Earth was born after the last human being left the moon. There is no one currently alive who has experienced what it is to stand on another world. The knowledge is preserved in recordings, in interviews, in the written accounts of the 12 men who were there. But the living human experience of it, the embodied knowledge of what it feels like to stand in a spacesuit on the surface of the moon with the Earth hanging in the black sky above, that knowledge exists in the memories of people who are in their 80s and 90s and who will not be with us much longer. When the next person stands on the moon, they will be the first to have that experience in 50 years. But they will not be able to share it with the 12 who came before, because those conversations across half a century of absence are not conversations between contemporaries. They are conversations between generations. This is what we gave up by stopping. Not just the scientific knowledge, not just the technological capability, not just the economic and strategic advantages. We gave up the continuity of human experience, the living chain of people who know what it is to be there, and who can teach the next generation not from records, but from memory. That chain was broken, and rebuilding it, reconnecting the people who will go next with the experience of the people who went before, is one of the most important tasks of the return. Now look at the moon again. Somewhere on its surface, in the Fra Mauro Highlands, in the Taurus Litrau Valley, in the Ocean of Storms, the equipment is still there. The retro-reflectors are still working. The abandoned rovers sit exactly where their last drivers left them. The flags have faded to white. The footprints will last for millions of years. Everything about the moon is exactly as it was when Cernan climbed the ladder and said goodbye. It has been waiting, not passively in the way that dead things wait, actively in the way that places wait for the return of people who have been there and want to come back. In the way that the Taurus Litoral Valley waited for the geologist Jack Schmitt, the only scientist to walk on the moon, to return and finish what he started. Studying the orange soil at Shorty Crater that turned out to be ancient volcanic glass, a discovery that opened more questions than it answered. Schmitt has been waiting too. For 50 years, he has advocated for a return to the moon, argued for the water ice at the poles, written papers and given lectures and testified before Congress. He is in his 80s now. He may or may not live to see another person walk on the moon. This is the specific human cost of the 50-year gap, not abstract, embodied in a geologist who walked on the moon and came home and spent 50 years trying to get us to go back. Now think about what comes next. The people who will walk on the moon in the coming years were not born when Cernan left. They trained for a mission to a world that no living person had visited. They will land at the South Pole, a place that none of the Apollo astronauts ever saw, because Apollo was constrained to the equatorial regions. They will find water ice that no human being has ever touched. They will stand in a place that has never held a human footprint. And if we sustain the commitment, if the political, economic, and institutional conditions hold better this time than they did after Apollo, they will be the first of many. The footprints they leave will be joined by more footprints. The base that was planned in 1969 and cancelled in 1970 will be built, slowly and expensively, at the South Pole, where the water ice and the near-constant sunlight make it possible to sustain a permanent presence. And, eventually, in the longest arc of the story, the one that spans not years or decades, but centuries, the moon will become what it was always going to become, the first stepping stone. The first place beyond Earth where human beings live and work and build, from which they launch deeper into the solar system, from which the expansion that may eventually reach other stars becomes possible. Or we stop again. The forces that ended Apollo have not been eliminated. Budget pressures are real. Political cycles are real. The difficulty of sustaining peacetime commitment to something that requires wartime-scale resources is real. The competition from other priorities, healthcare, education, defense, all the things that democratic governments do, is real. The outcome is not guaranteed. What is guaranteed is that the moon is there, that the footprints are there, that the retroreflectors are still working, still returning laser pulses from Earth, still measuring the moon's precise distance from a world that has changed enormously since they were placed there. And what is guaranteed is that the question of what we do next, whether we go back and stay, or go back and stop again, or find something in between, is a question being decided now. In the decisions being made about Artemis budgets, about SpaceX Starship development, about the Artemis Accords, about the commercial lunar economy, about how we respond to China's lunar program. These decisions are being made by people, specific, identifiable people, politicians who vote on appropriations bills, engineers who design launch vehicles, scientists who plan mission architectures, executives who decide where to invest, citizens who vote for politicians who vote on appropriations bills. The moon is not an abstraction. The decision about whether we go back and stay is not an abstraction. Both of them are real. Both of them are waiting. Come inside, but carry this with you. Somewhere on the surface of that object in the sky, there are footprints made by 12 people. Between 1969 and 1972, preserved perfectly in the fine powder of the lunar regolith. The footprints are evidence that we did it once. The 50-year gap is evidence that doing it once is not enough. The question is whether this time, when we go back, we stay. That question is ours to answer. The moon will wait. It has always waited.